Hello everyone. Welcome to the lecture of Fundamentals of Thermal Radiation. This is lecture 1. Before starting the lecture, let's understand what are the learning objectives. Well, I have prepared this lecture by taking a reference from book by Heat Transfer, a Modern Approach, written by Yunus A. Sengel. You can also follow that book for proper understanding and more elaboration. Let's understand what are the learning objectives of this chapter. The various things that you will come to know are understanding the electromagnetic radiation, that is the full spectrum of electromagnetic radiation, how a black body behaves and what is a black body, how to calculate the emissive power at a particular wavelength and temperature, as well as the total emissive power over the entire spectrum of electromagnetic radiation. Now, after that, we will come to know about black body radiation function, that is, what is the application of radiation function to calculate the overall emissive power. We will also come to know about the surface properties of any bodies, that is emissivity, absorptivity, reflectivity, and transmissivity. So let us start the introduction to the chapter called Fundamentals of Thermal Radiation. So as we know that, or let us say, as we have discussed so far, there are two modes of heat transfer which we already have discussed, that is conduction and convection. The third mode, and indeed a very important mode of heat transfer, is thermal radiation, that is heat transfer by radiation. Let us understand the mechanism of radiation. Heat transfer by radiation takes place by electromagnetic waves. Now, what is electromagnetic waves? As we all know, when a certain molecule change its electronic configuration, that is, it comes from a higher energy level to a lower energy level, then it emits certain photon of energy. These photons of energy are quantified by h multiplied by frequency of those waves, where h is Planck's constant, and these photons travels at a velocity of light. This all we know as per our 12th grade science syllabus. The first person who propounds this theory was James Clerk Maxwell, who said that electromagnetic waves are basically electromagnetic radiation which emits as a result of change in electronic configuration of the atoms or molecules. Now, there are two important properties related to electromagnetic waves. They are wavelength and frequency. And this wavelength and frequency are related by lambda is equal to c by nu, where c, as we all know, is the velocity of light in vacuum, which is equal to 3 into 10 raised 8 meter per second. Now, if we replace the medium, that is the vacuum, with some other medium having a refractive index n, then the equation 1 has to be replaced, then C in equation 1 has to be replaced by C naught by n, where n is the index of reflection of that medium. Unlike wavelength, which depends on the medium, on the refraction index of the medium, frequency doesn't depend upon the medium through which its travel. That is that is the frequency of electromagnetic wave doesn't depend upon the refractive index of the medium through which it travels. It only depends upon the source from which it comes out. Next, the energy that lies in an electromagnetic radiation. Electromagnetic radiations, as defined by Max Planck, are said to be a collection of discrete packets of energy, which are called photons. And each photon has an energy E is equal to h nu upon c, where h is Planck's constant and c is the velocity of light. In the entire electromagnetic spectrum, the frequency, or rather we should say the wavelength, can vary from very less, that is 10 to the power minus 10 micrometer, to more than 10 to the power 10 micrometer. The least wavelength are that of the cosmic rays, that is gamma, X and beta rays, and the most uh, longer wavelength are that of the radio waves. Nowadays we call them the power waves, because all kind of transmission, interspace transmissions, are being made by the radio waves. This is the spectrum that we are talking about. As we can see, the longest wavelengths are of the radio waves, and the shortest wavelengths are that of gamma rays and X-rays. The visible spectrum, which lies between 0.4 micrometer to 0.76 micrometer wavelength. Or if we talk about in terms of frequency, then it is 7 into 10 raised minus 14 to 4 into 10 raised minus 14 hertz. Let's talk about black body radiation. What a black body means. A black body can be defined as a perfect emitter and absorber of radiation. What do you mean by perfect emitter and what do you mean by perfect absorber? By the term perfect emitter, what we mean to say is no surface can emit more energy than a black body at a specified temperature and wavelength. Now, what do you mean by perfect absorber? A black body, or any body which absorbs all incident radiation coming from every direction and at various, or we can say at entire range of electromagnetic spectrum, is called a perfect absorber. Again, I'm repeating, a body which absorbs all incident radiation regardless of its wavelength and the direction from which it comes is called a perfect absorber. Now, how to quantify the energy that is being absorbed or that is being emitted by a black body at any particular temperature T? Whereas we have already said a black body doesn't emit or absorb radiation with respect to any particular wavelength lambda. That is, it is independent of wavelength lambda. Stephen Boltzmann's law, which will come to see in the later lectures, gives us the derivation of the quantity of radiation that is being absorbed or emitted by a black body, which is nothing but multiplication of sigma, that is Stephen's Boltzmann constant, which has the value of 5.67 into 10 raised minus 8 watt per meter square Kelvin to the power 4 into the absolute temperature T in Kelvin to the power 4. As we can see, there is no terms of lambda involved in this equation. Now, what is the term black refers to? A black body need not to be perfectly black. It is our perception, how we see it. Let's say we want a body which is a perfect emitter, that is, it emit energy at all wavelength and direction. Then we can take a charcoal as a reference. Charcoal can be referred to as an idealized blackbody behavior. That is, I have already written surface coated with lamp black paint approach idealized blackbody behavior. In one of the experiments that we will come across in our syllabus, we will see that if we want to calculate the emissivity of any surface with reference to a blackbody, then that blackbody will be taken as a steel plate which is coated by lamp black. This In this way, the steel plate will approach an idealized blackbody behavior. But on the other hand, there are some blackbodies which are perfect absorber, and they appeared quite white to our eyes. For example, snow and white paint, they reflect light and thus appear white, but they are essentially black for infrared radiation since they strongly absorb long wavelength radiation. So we can say that a black body need not to be ideally black to be called as a black body. It can be white or it can be perfectly black. It depends upon our use. If we want a body which can emit radiation, which can emit radiation to the max, then we will need a lamp black approach. We will need a surface which is painted by lamp black. On the other hand, if we need a surface which is a good absorber, then we can have snow or a white paint reflector on any surface. Now let's come to spectral blackbody emissive power. The term spectral blackbody emissive power means emissive power at a particular lambda and a particular temperature T per unit time, per unit surface area, per unit wavelength, about that wavelength. For example, if we want to calculate the amount of radiation that is being liberated by a light bulb, that is household light bulb, in the visible wavelength spectrum, then we can use this spectral blackbody emissive power to calculate the total amount of radiation. This relation is also known as Planck's law and is expressed by EB at lambda comma t is equal to C1 divided by lambda to the power 5 exponential C2 by lambda t minus 1, where C1 and C2 are constants, where C1 is equal to 2 pi h C naught square, where C naught is velocity of light, and C2 is equal to h C naught by k, where k is Boltzmann's constant. The equation 4 need to be changed if this emission is taking place through a medium instead of in vacuum. Then the constant C1 will have to be replaced by C1 by n square, because the term C naught involved in C1 has a power of 2. So C naught will be replaced by C naught by n, and hence C1 will be replaced by C1 by n square. Now next comes to Wien's displacement law. Before that, let us plot the spectral emissive power of a body at a particular temperature. Now we plot, then we will get a graph like this. Here in the y-axis there is spectral emissive power, that is EB with respect to lambda, and in the x-axis there is wavelength, and we have got several plots at different temperature. Let us say 100, 300, 500, 1000, 2000 till 5800, which is the average temperature of sun. Let's talk about this graph, the graph that is plotted for 100 Kelvin. We can see the graph as the wavelength decreases, the graph goes up to a maxima and then it decreases. And This behavior is shown by all other graphs at different temperature. Let's say if we increase the temperature to 300 Kelvin, the graph will show the similar behavior. That is, it will go up to a maxima and then it will drop. Again for 500, it will drop. If we join the locus of all the maxima, then we will get a straight line, and this straight line is nothing but the wind, which is quantified by Wind's displacement law, which we'll see in the next lecture, that is used to calculate maximum wavelength that can be emitted by a body at that particular temperature. Now, what are the other features of this graph? Let us discuss it by point to point. As we can see, this emitted radiation is a continuous function of wavelength. At any surface temperature, it increases with wavelength, reaches a peak, and then decreases with increasing wavelength. Point number two, at any wavelength, the amount of emitted radiation increases with temperature. As we have seen, that if the temperature goes from 100 to 300 to 500 to 1000, and if we take, let's say, a wavelength of 10 micrometer, then as we increase the temperature, the emissive power also increases. As temperature increases, the curve shifts to the left, to the shorter wavelength region. Consequently, a larger fraction of radiation is emitted at shorter wavelength at higher temperature. That is, at higher temperature, let's say from 100 to 300, 100 to 300, as we can see, the area of the graph is more in the region of less wavelength. If we take the reference of 100 Kelvin graph and the reference of 500 Kelvin graph, then we can see the portion of the graph that lies in the shorter wavelength region is more as compared to higher wavelength region. That is, as the temperature increases, more and more energies is being emitted in the shorter wavelength region. Number 4, this is very important. Let's talk about the topmost graph, that is solar graph. The radiation emitted by the sun, which is considered to be a black body, sun is a black body at 5780 Kelvin or roughly 5800 Kelvin, reaches its peak in the visible region of the spectrum. Therefore, the sun is in tune with our eyes. On the other hand, the surface at T equal to 800 Kelvin emits almost entirely in the infrared region, thus are not visible to the eye unless they reflect light from the other sources. That is, if we talk about the graph of solar sun, then we can see the maxima of this graph lies in the visible range spectrum. The visible range spectrum lies in between 0.4 micrometer to 0.76 micrometer. Hence we can say that sun is in tune with our eyes. That is, the radiation that is being transmitted by sun, the most of it is visible to our eyes. On the other hand, if we talk about the graph of 800 Kelvin, then most of the radiation emitted by a body at 800 Kelvin is in the infrared region. Hence, it is not visible to our common eyes. That's the end of the lecture 1. Now we will move to lecture 2 for more discussion on Planck's law and Stephen's Boltzmann's law. That is how to calculate overall emissive power of a body and the equation that governs the locus of all the maxima of this graph. Thank you.